All right, hello everybody. I hope the soldering stuff is going well. The checkpoints is due today. A lot of people have special cases, but if there's a lot of you who have not directly contacted me or Aaron about like any problems, then communicate like the time. So we're going to assume that you guys still have to like check it off today. If we'll talk about a little bit at the end, but just remember that is today. Yeah, so we're going to be talking about flight software today for those who are on track to finishing their soldering stuff or have finished and have started programming. This is kind of the bulk of the theoretical things that you're going to need to kind of get a drone flying. And not only that, at least like start from like turning motors and then move on to something that's, more of an engineering like perspective where you can actually like change some parameters and design your actual system. So
okay, yeah, so the type of feedback control that we're going to be implementing is PID, but Eric will talk a little bit more about that in a second. And let's start off with, since not very many people have experience with feedback control yet, especially since we have a lot of first years and second years who haven't necessarily taken like or completed EE3 or 141. And so the two primary types of feedback systems are open and closed loop ones. And so open is the most like basic type of feedback control, right? So you have your input and it gives a single output, and you have like some reading, and based on that reading, you just like input a value. So for example, like in EE3, like Eric can talk about a little bit more, but as for example, like a line following car, an example of like an open feedback system would be, oh, it's off the track to the left, so you turn to the right to get back on the track. And
wait. I don't think that's it. I think you're slightly off of it.
No, okay, yeah, wait, sorry, I'm getting mixed up. Open feedback would kind of just be like you telling the motor to turn.
Yeah.
Right. Yeah. It's just telling the motor to turn. That would, and so, yeah. And while closed loop feedback would be, I guess you'll end up doing it later in E3 in the form of like a PD controller, where you have your current error and then your derivative. So like a derivative of past values in order to like follow a line in a smooth fashion, right?
I think
yes.
Yeah, adding on to that, the way like so open feedback, I don't get misled. This isn't technically a feedback system. Open feedback just means the feedback system is open, meaning that doesn't exist. So open loop control system just means there's no feedback. So like what Maludi, which is this very, very good circuits professor, talks about is like feedback is something we see like everywhere. And that's how pretty much everything in the real world functions. So like, let's say you're like driving. Open loop control system just means that like you're driving with your eyes closed and you remember every single turn and how to get from home to like work or something. You have your eyes closed, and based off of just pure input without any feedback, you're driving. But then that obviously never happens. So then instead, just like with people, machines also need to have some kind of input that is a resultant of what their output is. So of course, if you see yourself driving a little too far on the right, then you want to adjust it, and that's what closed loop is. So we typically there's pretty much no modern system that uses pure open feedback.
Yeah, open feedback would kind of be like hard coding something. So like in MicroMouse, if you like hard coded your mouse to do specific turns and stuff, that's open. So it's like assuming that you know what needs to be done. And so our system is going to be controlling, using feedback control to account for the error or undesirable values that are found in several different aspects of our quadcopter. And an example of our input-output relation in our feedback control would be our input is the desired height. We would implement that through software, or by whether it be by like sending a signal over RF in the future, or right now, if you're just trying to get it to hover at a specific height, then that would be implemented through software. And the output would be the reading of the height, so the real actual height that's measured by the quadcopter. And we have similar feedback loops controlling all the different aspects of our quad. So we'll have to be able to control the roll, or like the tilt, and pitch and orientation and yaw and all of these different other aspects during flight. And the next slide will actually talk. Oh, I guess, okay, let's talk about the image on the right. So we'll see that the feedback elements are kind of like the error calculation, right? And that's summed with the input, and the controller and plant end up with, so the controller would kind of be like your algorithm, and then it'll be telling all of the different, like your 4 different motors to adjust the duty cycle of your 4 different motors. And then the plant would be like the response plus like all the noise that's accumulated during flight. And all of that information is then sent back in the form of feedback. And it's like a continuous loop during flight.
Yeah, and just to break it down, especially if you guys are watching this back when you guys are working, it's nice to see what each of these lines are kind of carrying. So your input, for example, let's just start with the very basics of hovering. You want your true up, your X, Y, and Z to be 0, right? So that's kind of what you want the input to be. Then you take what the actual reading, the measurement is, and then the feedback element here is probably negative. So something like a plus and a minus here. So then you'll get like the difference between them, and that's your error signal. The controller is what takes this number, this measurement that you have, and then changes it to an electric signal that tells the motors what to do. The plant is like the physical thing that is converting the electrical signal into a change in your output. So we'll be using these terms probably throughout this lecture, and also if we're discussing later on to talk about the different aspects of your drone.
Yeah, and so this brings us back to like the roll, pitch, and yaw. So roll is kind of like if you have a line going through your aircopter frame, roll would be like the tilt, right? And then yaw would be the rotation itself of the aircopter, and pitch would be if your aircopter was facing forward, it'd be like tilting up and down. Whereas, yeah, and roll is like tilting left, right. That makes more sense.
Yeah, and then this is also really important because like you've done in your past lab, the complementary filter output is outputting a vector that's relative to its own reference frame. So we want to be able to qualify the X, Y, and Z into a roll, pitch, and yaw, and use this for our control system.
And so this slide kind of relates the example feedback control loop, all the different parts, to what we're actually doing on our quadcopter. So we have your input in the image is a maneuver set point. So it's like what you want to do, like the goal value. And then the controller calculates calculates what each motor needs to be done, and then assigns the appropriate duty cycle to all 4 of the motors. And the plant is the processing for post adjustment, I guess you could say. And the motors are meant to manipulate and change the orientation of the quadcopter to match the maneuver set point. And it can't be done instantaneously, which is why we have that feedback control that collects your data from, in our case, an IMU, and brings that all the way back to be subtracted from the desired set point, and then repeat. And that brings us to the way torque works and the conservation of angular momentum on our quadcopter. So on the image on the right, you'll see that it's the same implementation on our quadcopter, where diagonally placed motors spin in the same direction. So like your front left and your back right will spin the same, back left, front right will spin the same, but each pair spins in opposite directions. And your motors actually have, I think, different colored wires depending on the spin direction. And if you plug them in backwards, then they'll spin in the opposite direction. So please don't do that. And the reason for that is because as your motors spin, they generate angular momentum. And in the case that all of your motors were spinning in the same direction, then your entire quadcopter would just continuously spin in the same direction that the motors are spinning. So
opposite direction.
Yeah. And so, like, for example, if the two green propellers were actually spinning in the same direction as the red propellers, then the entire quadcopter would be spinning counterclockwise. Yeah. And that brings us to yaw. So as mentioned earlier, yaw is like the rotation of the quadcopter. And in order to manipulate yaw, all you have to do is just have two diagonally adjacent motors spin faster than the other pair. And as shown in like the previous slide, what this does is it increases the, the angular momentum generated by a pair of motors. And so would anyone like to say what direction this quadcopter will spin in? The arrows are conveniently already drawn out. So if the green ones were to spin faster than the red ones, what direction, counterclockwise or clockwise? It would actually spin in clockwise because it's like opposite, because it's generating angular momentum in the counterclockwise direction. So the entire quadcopter, because of the conservation of momentum, it would spin in the opposite direction. So it'd be clockwise.
Like if your quadcopter was still, its angular momentum is 0, but then the sum of angular momentum across your bodies would have to be 0 too. It's like the high school physics stuff.
Yeah, so it's like opposite. And so that brings us to roll. So roll is like tilting left and right if your quadcopter were facing forwards. And in order to control roll, we employ a really similar principle. So since we don't want our quadcopter to spin, then we would just have, if we wanted to tilt to if you wanted to tilt such that your left, the right side of your quadcopter dips and your left is raised, then you would want to increase the lift on the left side of your quadcopter. And in order to do that, you just increase the motor duty cycle on the left motors. So it just raises it. And because of we'll bring back conservation of angular momentum, since the motors are spinning in the opposite direction, this will generate little to no rotation. Yaw. It'll generate little to no yaw. And pitch is controlled in an almost identical manner to roll, except this time you want to raise, in this case, if you want to raise the front of your quadcopter, then you'd increase the lift to the front and then decrease or maintain the same duty cycle to the motors in the back, such that the increased lift generated on the front motors will raise the entire quadcopter upwards. And so since roll, pitch, and yaw, they don't really affect each other, as shown in the previous slides, then we can control them we can manipulate and control each individual quantity. So your yaw, roll, and pitch can be kind of added together in a pretty linear fashion. And as Eric says, much wow magic.
Right.
And yeah.
Is this my part? I think it was my part, right?
Yeah.
So yeah, let's go kind of take a step back from the control system and kind of think, this is kind of something you would touch on in E3. This is how would you go about doing this, right? So the most straightforward and immediate idea of a closed loop system would be it would be called the proportional controller. What this means is, let's take this example. Let's say your drone starts tilting to the right. You'll notice this with your IMU. And what are you going to do? You want to, you notice that the vector is pointing away, then you want to make the right one go faster and the left one go slower. So here is just a sample code, for example. Take your left, you have this left input, let's just say it's a 0 because you want it to be 0 degrees. And you have your complementary filters X value. If X is positive, right, meaning that this vector is pointing to the right side, then you want your right ones to spin faster, so you add it on, and then your left ones to spin slower, and you subtract it. And this is probably how most people kind of start, understanding what control loops look like. However, another example that if you do E3, or if some of you guys go on to do Micromouse in the future, next year too, as possible, is a line following car, or like following the distance between your walls. Like the closer you get to one side of the line, the more your car would want to go to the other side. Or at least that's how you want to control it. However, there are a few problems with this. And we'll kind of talk about how we want to discuss it. One problem is that using only one variable makes it so that all the problems that might come with your control system, you only have one design parameter to kind of massage it and design it to be exactly for what your drone's qualifications are. And that's obviously a problem as a designer. Secondly, we'll talk about this in a little bit. Proportional controllers will pretty much always have steady state error, unless your plant is a little different. But in our case, it will always have steady state error. We're going to analyze these things called rise time, settling time, and overshoot time. And this is when you're kind of trying to tell your drone, oh, to reach this target. For example, if wind blew on it and then it started tilting, you want to tell it to go back to zero. The time it takes to respond to that, how long it takes to stabilize, how much it might like overshoot from its target. These are all qualities that we want to control, but they're going to be tied together because you only have one design parameter. And we'll see that there's often a compromise that will have to be made because of that. And lastly, this is a kind of specific scenario. In an ideal system, you would actually have oscillation with this type of controller. And we'll talk about a little bit about why as well. So going over the key concepts that I just mentioned. Steady state error is probably the easiest to understand. It is just that let's let your thing run for a while, and hopefully it'll stabilize to the target that you want to be, which is your input, because you want your error to eventually be zero or close to zero. And what steady state error is the difference between your input and your output at steady state. We're going to talk about this in a second, but integration of your error allows you to remove steady state error. And this makes sense because if you have some kind of bias, right, and it integrates and you're going to constantly be counting these errors, your drone will start to compensate for it and exert acceleration in the other direction. For the other thing is having we'll reference this constant called KP. I use this in the sample code too. K is always used as a constant, and P just means for proportional. So this is what we talked about in the most naive case. A higher KP will lead to less steady state error, and we'll talk about why in a second. So let's go back to like the most simple implementation, right? And the question here is it possible to achieve 0 degrees in steady state? I'm not going to ask you guys to answer this because it's a little hard to think about on the fly, but kind of you probably see that I'm foreshadowing that the answer is no. Let's take a look at why, right? So I think one place to start is, let's say that your motors are not going to output the same like torque given the same voltage. So your motors are all made unequally, right? So here, let's say your right motor is spinning slower for the same voltage. Then it'll start dipping to the right side. And then your air signal would make it so that your controller wants to push it back to the right side, right? So you're going to eventually have a steady state where your input is higher, your output is higher on the right side than on the left side. However, in order for this to exist, there has to be an error here that gets multiplied by the controller and the plant to create this value. So essentially this like adjustment doesn't exist without there being error like in place. Now, if you've worked with like the E3 cars, this isn't really a problem because let's say your car is like a millimeter to the left side just to adjust for it. That's fine because you're still going to be following the line. However, for our drones, this is a big deal because if you are constantly like 1 degree off in any of the axes, then, or like a few degrees off, then your drone is going to start flying in that direction when it's supposed to hover in place. The next thing we're going to talk about is rise time. And this is how fast your drone will respond to a change in input. And as I said, for example, if later on you're trying to implement it to move forward and back and have your own inputs, or if a wind blows and then you want to go back to 0, for example, the question is how fast does your drone respond to this change and move back to where it's supposed to be. So we want to obviously keep the rise time small so that it doesn't stay out of center for too long. And the greater the constant KP is, the question here, this I think will be easier to understand, is will it increase or decrease your rise time? So I'm going to ask for someone to answer this, even in chat or something.
Wait, what's the question again, Eric?
So we want this rise time, the time for it to go from like one position over to our target. So like if our drone is off axis and then we want to return to a target, we want to do it as fast as possible. So we want this rise time to be small. So the question is if we increase our KP, like our constant for the error, will this increase or decrease the rise time?
Joshua said decrease, which is correct.
Yes, exactly. So what will happen is we're going to multiply this error by a larger number, which makes it so that we're driving higher like duty cycle into our motors, making it drive faster and hopefully pushing it back up faster than if we didn't. So that is correct. Make it infinity, and we'll talk about why that does not work, sadly. Overshoot. This is the reason why you can't do that. Overshoot occurs when your controller has an input and you go past the target. And like John said, imagine if you had like this infinite power motor, it would like it would accelerate your drone to like go back to axis. But then when it's at 0, it'll stop adding anything. But you still have this angular like momentum going, and then you'll kind of overshoot. So this occurs when you go past the target that you want. The maximum overshoot given a perfect system will be 100%, meaning that you'll get to like 2.0 on this graph. And that actually means your system will oscillate, which we will talk about after. Of course, we also want this to be low because we don't want our drone to be constantly like switching back and forth. And also because we want our drone to always stay around the center level and not be like, way off, because there's a certain angle at which it's kind of impossible to recover.
Yeah. In addition, like this overshoot value, and like the damping behavior that you see in the image on the right, that's like an ideal situation, right? So ideally there's like no external factors that would affect the flight of your quadcopter. And so it can overshoot and then dampen itself out over time. But unfortunately in the real world, like whether a fan is blowing or your motor duty cycles aren't perfect, that overshoot can cause like insane oscillations if the conditions are really poor, and that can cause your quadcopter to do like a complete flip, and that would be suboptimal.
Yeah. The next thing I want to talk about is settling time. This is how long it takes to reach a stable state, and it's within 10% of, I believe, of your target. But I mean, 10% is arbitrary. The point is that you want to minimize it. This is especially important for us because the more time that you are off center, the more your drone will drift around. Kind of like how we talked about with steady state error. While it doesn't seem like a big deal for some other control systems to be off by a slight amount, the longer you are for off center for a drone, the more it will start veering towards one side. And in high quality drones, this is why you typically also have like cameras for control systems as well to make sure this type of thing doesn't happen. Of course, we don't have that. So talking about, this is something that was always interesting to me when I first started learning about control systems. And it's that, let's take the most naive situation again. Let's say every single time we veer to the right too much, so our angular position is too high, then we want to apply some angular acceleration with the propellers, right? So in an ideal world, let's say there's no other factors, and this was just like a pure mathematical simulation. That means take this extra, this should be an angle, so it should be like theta or something. I'll just use x here. So the second, is for those who know differential equations, the second derivative of x is equal to negative some constant times x. Now, if this this is a second order differential equation with no damping, and if this is familiar to you, this is actually the precursor to harmonic oscillation. It's kind of like if you've done high school physics too, how acceleration is equal to, for a spring, some constant times its position times -1. And if you were to leave it, it would just oscillate. This is obviously really bad because we want it to stay at one position. So that is, oh yeah, I should have, are my slides out of order? Where's the stability slide? Oh, wait, I skipped the stability slide. So yeah, this is where we actually talk about stability. Stability is how far away your drone is from oscillation. And we'll see why the PID, the proportional, integral, and differential control system, the differential part is very important to preventing it from oscillating, as well as integration helps improve stability. For us, we want to make sure that it's a stable system, again, more so than some other applications, because our drone might go crazy if it's not stable. Sorry, actually integration does not improve stability. The differentiation improves stability, if you guys are watching this again.
Integral and derivative are flipped, right? For stability.
Yeah, we'll see it in the chart later.
Okay.
So, yeah, so if for those who haven't seen this before, this is kind of the most basic level of control systems. When you get on into 141, this is kind of what you'll learn, but you also kind of get introduced to high level control systems that are just generic transfer functions and generic responses instead of this, specifically these operations. Proportional is kind of the present time. It will adjust the output based on its current error. Integral is a memory, so it's a sum of all past values, and it integrates over past values to find a past trend, and then uses that to also adjust the current error, the current output. And lastly, derivative is kind of a prediction of what's going to happen in the future. Use it to, for example, like for those of you who have worked with like the E3 cars, let's say your car is like coming in from the side because it was off center. Here, your position is going to be 0, so you're not going to cause the car to turn back, and it's going to keep moving forward. But when it's at the line, you actually want it to move this way. So what we're saying is, if it's moving to the left, we don't want it to move to the left anymore, and that's kind of what derivative does, because it predicts in what direction it's about to go. And especially in inertial like systems, like we have, the derivative is a good variable for that. So yeah, so we're going to kind of talk about this. Might be a little bit like hard to keep track of. So feel free to go back on the slides as well as the recording to kind of get this in your head, because starting from here, there's always I'm going to have a little bit of talk about this, because there's always going to be people who want to like find the solution. But when it comes to like engineering these kinds of things, it's more important to understand where these things come from. And I actually hear this a lot from recent like classes. Just understanding where things come from, because we don't want to like have to calculate every single thing. Not only that, like drones are highly nonlinear, because obviously it's, well, first of all, it's circular, and there's also different electrical factors and stuff like that. So it makes it so that our analysis isn't always completely right. So it's more important to understand what each of these constants kind of do for our system. And this will also help you guys do it without having to fully calculate and characterize the physics of a drone, because that's honestly not a good use of time. For proportional control, the output is directly proportional to error, like we talked about. One thing we're talking about, right, is what will happen if we were to increase this coefficient. Now, we already talked about how rise time would decrease because it will reach its target faster. We talked about how overshoot will increase because it will attempt to reach its target faster, but then it won't stop it and it'll just keep going. And lastly, it'll decrease steady state error to step responses. It will still exist, but it will decrease it if you increase your coefficient. And that's because it will take a smaller error to create the same steady state, basically. So yeah, one of the problems we see here is that we said that we want to decrease rise time and overshoot, but we can't satisfy, as well, and stability I didn't really talk about here, but it also decreases stability, and it's related to this situation with overshoot mathematically. But we can see that we kind of cannot satisfy both a low rise time and a low overshoot, as well as a stable system as a designer if we only had this proportional controller. So the other tools we have are the integral. This just removes the steady state error. It mathematically functions very similarly to the proportional controller, where it increases overshoot, decreases rise time, increases settling time. That is actually one of the different things, whereas for proportional controllers, it doesn't really do that. Oh yeah, and does increase stability, yes. Then we have derivatives. So this is important to us, especially. It reduces our overshoot because as we're kind of moving away from it, it'll figure out like which direction it's moving and kind of reduce that. However, at the same time, it will reduce rise time, kind of the same trade-off, but it reduces it at a much smaller degree than it reduces overshoot. It will increase the settling time as well because it'll prevent it from going back to like the center, because whenever the value is changing, it tries to prevent it. So that's what this point kind of is the key to everything, is it aims to keep the derivative low. And the effect of this is it'll create a smoother flight. And that's definitely something we want, especially when we have like noisy input signals and stuff like that. This is very helpful. So sometimes we might want to implement derivative. This part here, the last 2 points are kind of just to show that these aren't like set in stone rules. You can kind of control it however logically makes sense, and that might have different effects. So sometimes some people like to implement derivative just on the measurement, so what your vector is, as opposed to the derivative on your error. So it's the measurement minus your input, let's say if you're trying to make it move and stuff. And the reason for this is because it's more practical, because you're trying to stabilize like the movement as opposed to reacting as well to your changes in input. This won't be too important for you at first, but if you go into including inputs, then yes, this will be pretty important to try out. This second part will be important to every one of you. Your values are discrete, so your question is kind of how do I implement a derivative? You can implement the difference as well as time if you wanted to, but then again, time is also just a constant factor most of the time. So you can implement the difference between the last measurement and the current measurement, and this will allow you to kind of model a derivative. However, this will be pretty prone to high frequency jumps. For example, if you had your vector suddenly move or something like that, and any noise that's involved, it might create drastic effects on how you control your drone, and it might mess it up. So the other way you can do is to average across multiple values, which you really have to test to see if which one works for you. Here's like a good table. It's a good rule of thumb. I did mess it up. I was pretty sure I messed up the slide. So your integral does not help your stability. Your integral definitely makes it worse. Derivative is what improves the stability because it wants it to not oscillate. Basically, it's a damping factor. So yeah, this is a good table for you to see. This is kind of the idea. If you see your drone is oscillating a lot, and you kind of have to tinker, for example, with the overshoot amount by decreasing these, maybe increasing this. And it'll be a trade-off in all senses. And at the end of the day, you just have to get a range of values that actually works for you. So this will be very useful for you guys, hopefully. And this is kind of a sample for like how you would go about implementing it. So it's the same thing. You get your sensor fusion code, you figure out what your vector is, and you take the different your error and multiply by some constant. You keep track of, for example, what your differential error is, multiply some constant, and then this multiply some constant, and then you'll do this for all your motors. And at the same time, kind of like we talked about, you can kind of add it up for each motor depending on which direction it's supposed to move. Then you want to update memory because you have to keep track of what the values are for integrals, as well as if you're averaging derivatives. And then you have your motor driver code that actually makes it run. Cool. That's the whole thing. So does anyone have any questions so far? I know that it's probably pretty abstract, and even like real control systems engineers, there is a level of intuition that goes with it.
So here you watch it later, right?
Huh? What did you say?
David?
Hello? He's gone.
I think he said something about if it's going to be uploaded later. And if that was his
Oh.
question, the answer is yes.
The answer is yes. We can go. Yeah. Yep.
One thing, I guess like one thing about the like your array of values, like a buffer to an extent, like your memory, is you'll have to, as Eric mentioned earlier, like finding a balance between the size of that buffer is going to be pretty important, because our MCU, it's like fast, but it's also not insanely fast. So you'll have to keep in mind of all of your derivative and integral calculations utilizing all the values in that buffer. So
yeah, I have another slide on that, so we can talk about
yeah.
that a bit. Okay, if there's no questions, we'll move on to logistical stuff. First one, most people are still working on soldering. There's a lot of stuff happening with people's parts coming late and people's like tools coming late. A lot of people have messaged us directly, which we really appreciate and it's really helpful. A lot of you guys also didn't message us, considering that the thing is due today. So I know everyone's working at their own pace, but in the next 2 days, make sure to message me and Aaron, because we don't want to have to go around texting everyone. We're also pretty busy. So make sure to message me and Aaron in your team chat with your updates. So I'm expecting just like all 3 of you or all 4 of you just have like a message saying where you're at. It doesn't have to be long. I just want to catch up. There are some special cases who talk to us about the deadlines that are okay. But that doesn't mean that the rest of your team is okay. Okay. So like, so especially since a lot of you guys are like, okay, all of you guys are soldering. You guys are all working at your own pace. And yeah, if you're soldering, you should be telling us what is happening. Checkoffs do not happen just by posting info into the drive or like finishing and waiting for us to like talk to you. If you don't tell us what's happening, we're going to consider that you haven't done it yet, because we can't, message everyone of you, and we're not going to check like every team's slide every day. Sorry, every team's drive every day. So that being said, just honestly, just let us know. And honestly, if for too long people don't talk to us, we'll reach out beforehand, but there's a possibility of dropping just for logistical reasons. And the next lab will post in the coming days. I've been kind of swamped, so I've been a little slow on that, but it will definitely be out soon. And considering that most of you are still soldering and also having problems with programming, hopefully that will be the next focus for you guys. Okay, this is for later on when you guys do start working with the drone. These are really, really, really important safety concerns that you have to consider, especially since it's not in person. We can't like watch over you guys like we do in the lab normally. So here are a few things. One is, don't ever put in code that doesn't terminate. You should always have code that will stop at one point. Even if you have code that, like after like 10 seconds just delays for like 5 seconds, that might even be helpful, but still at the end of the day, try to implement some termination. If you're not sure about it, just implement the termination and also include like a delay every 20 seconds or something, or 10 seconds.
Exit 0 or something.
Yeah. And that way, and before you do that, always try to set your motors to 0 before you do exit, just in case it gets hung in like an arbitrary process. Now, if your drone is spinning, you can't stop it, like, and it's running with code and you don't have code that stops, it's one of those moments where you're like, you really don't have anything you can do. You can kind of just wait for it to like, just dodge it and wait for it to fall or something.
Just like trying to stick your finger in a blender.
Yeah. So please do that. Secondly, always test your motors without propellers, just in case things get shorted. It might go way faster than you expected. There's just a lot of potential problems. Always test it before your propellers. If you're testing for flight, make sure that your drone is tied down with the string. And that's one thing, especially we can't watch over you guys this time when we normally have it in the lab. And always start with like a very slow setting. At most, start with 15% max power. If you can, just honestly work your way up so that you know what the power of your motor is. Wear eyewear. If you have safety goggles, great, or glasses, great, but even sunglasses can make a big difference. You never know. And yeah, just please follow this. We definitely do not want anything happening this year, and that's by far the most important thing to us. So this is like the most important slide. A lot of your members are also not here, so if you guys know that other people are going to start working on it, make sure to spread the word and remind each other, because this is just more important than anything. Cool. Here are a few tips for programming that you have to remember. The performance matters. So you have to write like good code. Don't like, oh, you can try brute forcing at first, but eventually you want to go through and try to optimize it. An example of this that's just like straight off the top of my head is, for example, if you're implementing integration, you can implement it like hard at first, but if you know how to optimize it immediately, just do that. So as opposed to integrating every single time and counting up your array, maybe just take off your old value and subtract it from like a running integration. You just subtract the old value and add the most recent, get rid of the old value from the array and add the most recent to the array, and just to keep track of it. For averaging your differences so that you don't only take like the difference between two, it's the same idea. Yeah, and then play around with it. So like, especially with, for example, the differences, like there's many ways you can go about processing that signal. You can take the derivative across all the points. You can take the difference and average those differences, the size, everything. And trying to understand why your drone isn't working and trying things that might be different, especially keeping in mind the design principles we talked about, will help you gain a lot from the experience by trying to figure something out. Secondly, especially for like the hardware coding problems, like definitely Google stuff, because that's kind of a software that's provided by someone else, and these things often happen to other people. Definitely ask us too if you're stuck, but try to Google first, because most of it will be out there, and most of the time if you guys come with really specific stuff, we're going to Google it anyways, just to make sure. So just Google it first. We're going to Google it and try to put our input, but like,
yeah, we're going to be Googling it too.
Yeah. So especially debugging SC-Link problems, try to look it up. And also make sure to read, if your SC-Link isn't working, stuff like that, read the error message and try to figure it out. Like I know Tim did a really good job with that, where he had a problem with his reset, and we took a look at that, and then we found out what the problem was. So a lot of the problems are like there in the hardware. And definitely working together. Like I said, none of these like control systems are purely set in stone. You guys can find ideas for each other, look at each other's problems. Everyone's having kind of different issues because you have different drones, and having a fresh eye to look at it definitely will help. So yeah, that's it for today. Oh yes, Aaron's meme. He let me present it. I just thought this was pretty great. You guys should appreciate it. This is me and Aaron. You can decide which one's who. And then this is you guys, except I can't see you guys. And yeah.
Thank you, Tim. I saw that.
Yes, thank you. Yeah, that's it. Anyone have any questions? Let's first have questions regarding today's lecture and logistics and stuff that regard everyone. And then if you guys still have questions about, wait, let me check real quick what the, okay, we have like 13 minutes for our officer meeting. So if you have any questions about the work you've been doing right now in soldering, or if you just want to update us, please do that as well.
We use headers for the radio too.
Yes. Use headers, please.
Oh no.
I think we packaged a lot headers for everyone.
Yeah. It's also just easier for you because if you solder it on, it'll be really hard to debug other stuff.
Yeah, it'll probably get in the way of your button.
Mm-hmm. Oh no, headers. Oh no. Did I not talk about this? Headers are they're like the bar.
It's like these things. Oh shit. Fuck.
Yeah, but they're like a bar of things, and they have like pins coming out one side, and these are female headers, female and male. So it's like
it's like these.
Oh, you haven't done it, so thank God. So
yeah,
for anyone
the female
working on it, yeah, what Aaron's showing, they'll have like a holes on top. You'll use like pliers or scissors, and you can cut them, or you can break them by hand as well, to make it like the right number of like squares, and then that you plug. You solder those on. Don't solder the IMU and the radio directly. You will like.
Yeah, it makes it really convenient because then you can plug and unplug them as you need.
Yeah, and that way you can still probe at other things. Yeah.
Yes, I found it.
Any recommendation for a good probe?
Good. I thought you had the 82. Just use
I don't know. Don't
Yeah,
you
you
just
do.
like stick live wires in the 82?
Yeah.
Yeah.
Just use the scope
kinda jank.
function.
Wait, does the 82 not have like the MIDAC thing where it also has like the multimeter? in?
Yeah, it doesn't have multimeter function. You have
Oh,
to build
that
a voltage divider in order for it to do that, which is really stupid.
Yeah. Yeah, just use 82 and just stick actual wires on it. It's fine.
Yeah.
Okay.
I'm surprised
So-
they're moving away from MIDAC though.
Some of my
Yeah.
MCU pins are kind of bent, so it's okay if I like try to bend them back,
They're
right?
just in the back. It's fine.
Yeah.
Just yeah, be careful.
Yeah.
Anything else? So yeah, a lot of you guys don't exactly have been checked off yet. So yeah, but so a lot of you guys have special cases, but even if one person in your team has a special case, the rest of you guys, I am expecting to see stuff either today or for you guys to tell us if it's not ready.
There you go. I gave you my.
Thanks.
Thank you.
That is a good reason, David. That is a very good reason. I will accept that.
I can give you the CS30, my CS32 code.
Oh no, I just got it done before this meeting.
Oh, nice.
So yeah, that was my entire Tuesday.
Okay, does no one have any questions? Is it? I have a feeling that no one has questions because no one understood. Because this is a little bit.
Yeah. No,
So what-
everyone's done EE3, so they understood.
Oh, sorry. I have a question. What does that last slide mean? I didn't.
This one.
Yeah. What does this mean? I don't
I'm not going to explain it to you, John. You either get it or you don't.
know. God damn it.
Yeah.
Okay, I'm gonna stop the recording then on that
Yeah.
note.